this section, we're going to look at applications of the definite integral. I've combined these two sections from the book into one because they're basically the same topic. They're just split up into two different sections. And one of the main things that I want to convey to you is how we use area to determine an accumulation of a rate. So for example, let me draw this little example to get us going. Let's suppose that you have a time axis, and this is in hours, and that the vertical axis represents a velocity or a speed. Let's say it's the speed of a car. And let's say that your car is going at an average of 50 miles per hour. In fact, it's more than an average of 50 miles an hour. It's a constant 50 miles an hour. Let's suppose you're on the interstate and you've set the cruise control for 50. Then the velocity function is a constant straight horizontal line going the length of time that the car is driving at that speed. Then the question is, how far have you traveled in 2 hours? Well, this one is in a straightforward, simple one, right? 50 miles per hour times 2 hours is equal to 100 miles. Graphically, what that looks like is the area under the curve between 0 and 2. And because the speed was a constant 50 miles per hour, the shape formed is actually a rectangle. And this makes perfect sense. The area of this rectangle is 100, which is 100 miles. And so we accumulate when we go from left to right. This time we're going from 0 to 2, and then we're taking the area under the curve. Now what's interesting about this is that this isn't really a coincidence. I can also do the same thing if I have some other curve like this. And I want to accumulate from 1 to 2 here, and the car is going slow here, and then it's speeding up, and then it has to slow down, and then speed up again, and then slow down. I can still accumulate area under this curve, and the area accumulated is equal to the distance traveled. And it's the same idea. But now the question is, well, how do you compute the area under a curve when it's all squiggly like that and it's not just a straight line? And that's where calculus comes in. We're going to take the integral under that curve to determine the total distance, or the total accumulation. This time what you're accumulating is distance, and in other examples we're going to accumulate snow, and we can accumulate rainfall, and we can accumulate money, all sorts of things. But the key here is that the curve that you have is a rate, meaning that it is some sort of derivative, and then what you accumulate is the antiderivative, or at least it's related to the antiderivative, and whatever that antiderivative unit would be. So let's take a look at this section, the definite integral as an accumulation function. Example number 1, snow began falling at midnight. So we're going to mark that as t is equal to 0. The rate snow was falling in inches per hour is given by the function s of t is equal to t minus 1/4 t squared, where t is the number of hours since the snowfall began. What time did the snow end? Well, we're going to assume that the snow ended when the rate of snowfall was equal to 0. And when would that be? So I'm going to set t minus 1/4 t squared equal to 0. And we're going to solve this for t. So I'm going to factor out a t. That leaves me with t times 1 minus 1/4 t equals 0. Split it up and we get t is equal to 0, which was midnight. And then 1 minus 1/4 t is equal to 0, which is t is equal to 4. So what time did the snowfall end? It ended at 4 a.m. But the more important number here is that t is equal to 4. Question B. how much snow accumulated in those hours. So if we look at a graph of the little s of t function, we know it's a parabola that has a root at 0 and at 4. And it's a downward facing parabola. So it looks something like this. The accumulated snow is equal to the area under the curve. And I want to calculate that. So we're going to say snow is equal to the integral from 0 to 4, those are my time values, of the rate of change function, which was t minus 1/4 t squared dt. And now we take the antiderivative. So this is going to be t squared over 2 minus t cubed over, and I need to divide by 3, but there was already a 4 there, so those multiply to give me 12. We evaluate from 0 to 4. And this is going to be 4 squared over 2 minus 4 cubed over 12. And then a new set of parentheses. 0 squared over 2 minus 0 cubed over 12. In fact, any time that your antiderivative is a polynomial with t to positive powers and then maybe some multipliers or divisors that are just numbers, and you evaluate that at 0, then this piece over here is always going to be 0. And this is an application, so let's work it out to 2 decimal places. This is 2.67 inches. So that's how much, that's the amount of snow that fell between midnight and 4 a.m. Example number 2, find the area bounded between the curves f of x equals 2x plus 1 and g of x is equal to 4 minus x squared. So what we want to do is we want to find the bounds that create a bounded region by these two graphs. And basically, we can sort of look at the equations and see what they're going to look like. The 2x plus 1 is a line with a slope 2. And then 4 minus x squared is a downward facing parabola that looks something like that. And here we can see the two boundaries, here and here, and it creates this little region here. Now that's not enough for me to figure out what the numbers are, but it gives me an idea about what I should be looking for. To find the exact values where they intersect, set each function equal to each other and solve for x. So we get 2x plus 1 is equal to 4 minus x squared. We have a quadratic, so we're going to move everything to the left. And we get x squared plus 2x minus 3 equals 0. Then we factor. We have x and x. We have 3 and 1. We'll use a positive on the 3, a negative on the 1, and that gives me the solutions of positive 1 and negative 3. And that's what these numbers were here. So this is 1 and this is negative 3. So we're going to integrate from negative 3 to 1. So we're going to have area is equal to the integral from negative 3 to 1. Now, Whenever we find the area between two curves, we always integrate with the top function minus the bottom function. Top minus bottom. Because we are looking for an actual area, we need the integrand to always be positive. And if we take the top function minus the bottom function, then this is always positive. Now, which function was on top in this picture? Well, it's the parabola. So this is going to be 4 minus x squared, because the parabola is on top, minus the line, because the line is on the bottom. The line was 2x plus 1. Be sure and use parentheses, and because you're going to have to distribute your negative, so you don't want to mess up the negatives on all this. And let me write it up here. So this is going to be the integral from -3 to 1 of negative x squared minus 2x plus 3 dx. This is equal to -1/3 x cubed minus x squared plus 3x. That's the antiderivative. Then we do the evaluation. So we get -1/3 times 1 cubed minus 1 squared plus 3 times 1 minus -1/3 times -3 cubed minus -3 squared plus 3 times -3 and that's equal to 32/3. Example 3. Find the area bounded between the curves j of x is equal to x cubed minus 6x and k of x is equal to x squared. So k of x is the red function here, and j of x is the blue, sort of purplish function. And what we're looking for is the area between the two curves. Now the problem here is the following. We can see the bounds here are going to be -2, 0, and 3. And I'll show you how to do that algebraically in a moment. But the issue here is this. Between -2 and 0, the j function is on top of the k function. But between 0 and 3, the k function is on top of the j function. So that means we can't just set it up as one integral from -2 to 3. We have to do two separate integrals, compute their area, and then add those two areas together. So our first step is to find the bounds. I've told you what they were, but let me show you how to find them algebraically, just for reference. So you set j of x equal to k of x. So that's x cubed minus 6x is equal to x squared. Move the x squared to the left. We get x cubed minus x squared minus 6x equals 0. We need to factor, but first we're going to factor out an x. That leaves me with x squared minus x minus 6 equals 0. Factor the quadratic. We get x and x. We get 3 and 2. Subtract to give me 1, and I want the 3 to be negative and the 2 to be positive. So that gives me x equals 0, x equals -2, and x equals 3. And those are our bounds. Now let's go ahead and call this I1 and I2 for the integral 1 and integral 2. You can call them A's too, doesn't matter. And so the total I is going to be I1 plus I2. Now we compute these separately. So I1 is going to be the integral from -2 to 0. And then it's j of x minus k of x dx. And then I2 is going to be the integral from 0 to 3 of k of x minus j of x dx. And we just compute these separately and add the result. So for I1, it's the integral from -2 to 0 of x cubed minus 6x minus x squared dx. Take the antiderivative of that, we get 1/4 x to the 4th minus 3x squared minus 1/3 x cubed, evaluated from -2 to 0. So that would be 1/4 times 0 to the 4th minus 3 times 0 squared minus 1/3 times 0 cubed. All that's going to be 0 minus, I'll tell you what, I'm going to go ahead and put this on the next line, minus 1/4 times -2 to the 4th minus 3 times -2 squared minus 1/3 times -2 cubed. And all that is equal to 16/3. So that's our result for I1. Let's take a look at I2. And so this is going to be equal to the integral from 0 to 3 of x squared minus x cubed minus 6x dx. And that is 1/3 x cubed minus 1/4 x to the 4th plus, because the negatives distribute, 3x squared. All of that evaluated from 0 to 3. So this is equal to 1/3 times 3 cubed minus 1/4 times 3 to the 4th plus 3 times 3 squared minus 0. Evaluation of 0 in a polynomial is 0. And that is equal to 63/4. And then we put it all together. So the total area is 16/3 plus 63/4, which is equal to 253/12. Next, we want to look at net excess profit. Basically, this one comes down to the situation where you have two investment opportunities. And one of the investment opportunities has a profit that is growing at a certain rate. The other one has another rate at which it's growing. And if you choose to invest the one with the higher rate, then the question becomes, well, how much extra money are you getting by making that choice over the profit that has a lower rate of change? And whatever is sort of extra is called the excess. And this is net excess profit. Example 4 says, for t years from now, investment A will generate a profit at a rate of P prime A of t equal to 20 plus t squared $100 per year. Similarly, investment B will generate a profit at the rate of P prime B of t equal to 30 plus 3t $100 per year. Question A, for how many years will the rate of profitability of investment B exceed that of investment A? So we want to know, when will the rates sort of trade places? So we're trying to solve this question here. When is PB prime of T greater than or equal to PA prime of T? To solve an inequality like this, we first arrange it so that it is compared to 0. So I'm going to move the PA prime of T to the left, and that makes it greater than or equal to 0. Then we solve this inequality. Now we have to use some the sign chart and stuff to solve this inequality because we're dealing with a quadratic in one of the functions. So the way you solve that is, first you set them equal to 0, or set the expression equal to 0 rather. And then you solve that for t. So this is going to be 30 plus 3t minus 20 plus t squared equals 0. If I simplify this, I get a negative t squared plus 30t plus 10 equals 0. I can multiply through by a negative. And now I can solve. So t and t. And then what two numbers multiply to give me 10 and subtract to give me 3? That would be 5 and 2. Negative on the 5, positive on the 2. So my two roots are t equals negative 2 and t is equal to 5. Well, t equals negative 2 doesn't make any sense in this case because that would be back in time. So we have t is equal to 5. Now we just want to verify that 5 is where the two investments trade places, and we need to verify that between 0 and 5, PB prime is greater than PA prime. So to do that, we just do a little sign chart. The sign chart starts at 0 and goes up to 5. This was my 0. And then I need to test a value. So I'm going to pick 1. And what I'm testing it in is the reduced form of the equivalent inequality right here. So it's this, which I can use that one right there. So if I plug in 1, I get negative 1 plus 13 is positive 12. So this is positive, and then the multiplicity was 1, so that is negative. Now recall that we were trying to solve for whenever the inequality is greater than or equal to 0, which means positive. So it is, in fact, this interval right here from 0 to 5. So that does say, for how many years will the rate of probability in investment B exceed that of investment A? It's for the first 5 years. And then question B, compute the net excess profit for the time period determined above. So the net excess is going to be the accumulation of profit that you received from investment B minus the accumulated profit that you would have received from investment A. Let's draw a picture. So here's time. This goes out to 5 years. And one of the investments is a parabola, and it starts at 20. The other one starts at 30, but it increases linearly, and they intersect right here at 5. Pretty close. And so what we're accumulating is this area between the two investments. So the net excess is the integral from 0 to 5, because we're integrating from 0 to 5. And then it's going to be PB prime minus PA prime. Because again, we take the top one minus the bottom one. And then we work this out. So we're going to get the integral from 0 to 5 of 30 plus 3t minus 20 plus t squared dt. This would be the integral from 0 to 5 of negative t squared plus 3t plus 10 dt. Find the antiderivative. So it'll be negative t cubed over 3 plus 3t squared over 2 plus 10t, evaluated from 0 to 5. And that would be negative 5 cubed over 3 plus 3 times 5 squared over 2 plus 10 times 5 minus 0, which is equal to 45.833333, etc. And this was in hundreds, so we're going to multiply that by 100. We're going to get $4,583.33. And that represents the profit, the extra profit that you get by investing in B over the first 5 years than you would have gotten by investing in A. The next topic is the Lorenz curve and the Gini index. Now, they use the Lorenz curve as a measurement of income and wealth distribution in a country or society, or however they want to define the parameters. So measurement of wealth / income distribution. And I'll call it L of x is the function. And what this is this is the cumulative percentage of total family income received by the bottom X percentage of income earners. So basically the scenario is this. You're going to take, let's use America for example, United States. You're going to take all of the income earners, all of their families, and you're going to line them up from those who received the least to those who received the most. And then you're going to mark off different sections. So you're going to take the bottom 10% of income earners, and you're going to take how much income they made cumulatively in a year, and you're going to use that as a percentage of the entire income of the entire United States. That's what the L of x gives us. Okay. Now, because of the way that it's sort of set up, there are several properties that must be true. The first one is that L of 0 must be 0, right? So if you line everybody up in order and you look at nobody, then there is no income to be considered, right? And they do these on a 0 to 1, so 1 is 100%, right? If you take L of 1, that's equal to 1, because you line everybody up, you look at everybody, And everybody has all of the income, so that's all of the income divided by all the income, that's 100%. And then number 3 is L of x is always less than or equal to x itself. What that means is that the X percent of the bottom wealthiest people, because we're looking at the poorest, the bottom, they can't earn more than that percent of the entire wealth. Because if they did, they wouldn't be the poorest, they would be on the wealthier side. So that's just an ordering issue. All right, now if we look at the graph of a typical Lorenz curve, right? So it goes from 0 to 1, 0 to 1, right? Here's x, here's L of x. It has to start at 0. It has to end at 1, 1. And it has to be less than x itself. So it can't be greater than this curve here. So it has to be under that curve. So one typical expression for L of x might be something like this. And so let's use this as an example right here. Let's say that that point is 0.3 on the x-axis and 0.1 on the y-axis. Then that means the bottom 30% of income earners cumulatively earned only 10% of the total income. And that's your typical Lorenz curve. So it's a way of measuring how a society or a country has its wealth and its income distributed. So we could talk about some of the extremes. We could talk about absolute equality. Absolute equality would be when everyone has an equal income throughout the society. Well, if that's true, then the bottom X percent must have the bottom X percent of the income. So in other words, L of x is equal to x. And the curve is exactly that line that was the upper boundary for what we were talking about, the green curve and the one above it. That's absolute equality. Everybody is equal. Everybody gets the same percentage of wealth. The opposite end of that is absolute inequality. In absolute inequality, L of x is equal to 0 for all but one last person who owns everything. So this graph would be, it's all 0, and then boom, right there at the end, one person owns everything. Sort of a dictatorship type scenario, right? Where all the lay people, they own nothing, and then the king or whatever owns everything. That's your Lorenz curve. Now, what can we do with the Lorenz curve? Well, an Italian economist around the turn of the 19th to 20th century named Gini came up with a way of interpreting the Lorenz curve to make more measurements. And so the Gini Index is what they call it now, is a measurement of income concentration. And it measures the difference between absolute equality and the Lorenz curve. As a ratio to absolute equality. So let's look at an example here. Here's one, here's one. Here's that perfect line again, right there. And then we're going to have the Lorenz curve. Maybe it does something like this. Like that. So what we're looking at is the difference between the absolute equality line, y equals x, and the Lorenz curve. And so here's the Lorenz curve. And then here's y equals x. And we're looking at this area here as a ratio of the area formed by the triangle, which is the area completely under y equals x from 0 to 1. Well, again, we're looking at area. To look at area, we need an integral. So here's the formula, or at least the derivation. The formula will come at the end, of the Gini index. You need to take the area between the Lorenz curve and the absolute equality. So this is going to be the integral from 0 to 1. Absolute equality is the function x. The Lorenz curve is L of x. So you subtract those, find that area, so that's a dx, and then divide it by the entire area of the triangle that's formed down there. That's the integral from 0 to 1 of x dx. That would be the one that results if we used just the entire triangle and found its entire area in that space. So the integral on top stays the same. And then I'll leave it to you to work out that the integral from 0 to 1 of x dx is a half. And then since you're dividing by a half, you can change that to multiplication by 2. So it's 2 times the integral from 0 to 1 of x minus the Lorenz curve L of x d of x. That is the formula for the Gini index. You should memorize that one. Example 5, the Lorenz curve for a small country is L of x is equal to x to the 2.1 power. Compute the Gini index for the country. So the Gini index would be the integral from 0 to 1, 2 times the integral from 0 to 1, of x minus x to the 2.1 power dx. This would be 2 times the integral of x is 1/2 x squared minus the integral of x to the 2.1 power is x to the 3.1 power divided by 3.1, evaluated from 0 to 1. And so we get 2 times 1/2 times 1 squared minus 1 to the 3.1 divided by 3.1 minus 0 is equal to 0.355. Next, let's talk about the average value of a function. So if you have a discrete set of data points, where you can just list them 1 through 8, 1 through 12, 1 through 100, as long as there's a finite number of them, you just add them all up and divide by the number of terms that you have. That gives you the average. But what should you do if you have a continuous function with infinitely many points? Well, you can sort of approximate this by taking a certain number of the points inside the interval and then averaging those, and then increasing the number of points that you take the average of, and to get a better average, and then you can keep increasing the number of points that you take. Well, as you do that, and you take more points and more points, that becomes an integral, because it's really the limit of a Riemann sum. So we could prove that, we could show it, but let's just get to the formula. The average value of f over the closed interval from a to b is equal to 1 over b minus a times the integral from a to b of f of x dx. So if you're thinking about this as an average, you can sort of think about this as the quote-unquote number of terms, right? Because it's the space that we're computing the average over. And you can think of the integral part as the sum part. Just like we were summing up areas of rectangles, it has a sort of nice analog to that. So it is the sum divided by the number of terms in that sense. Example number 6. A company's researcher determines that sales T months after a new toaster model is introduced to the market in thousands of dollars will be S of T is equal to 48T over the square root of T cubed plus 12T plus 4. Calculate the average monthly sales for the new toaster over the first year after the introduction. So I'm going to use the formula, but now you have to notice one little thing here. T is measured in months, and we want the first year. So that tells me that we need to go from 0 to 12, because there's 12 months in a year. And yes, we start at 0, because if we start at 1, then that's starting in the middle. You always start at 0 when you start counting and going forward like this. So the average value is going to be 1 over 12 minus 0 times the integral from 0 to 12, 48t over the square root of t cubed plus 12t plus 4 dt. Now notice that we can't find the antiderivative of this one. We don't know how to do that one. We might think about using substitution, but we have t cubed in the bottom with a square root, not t squared. And a t cubed would produce a t squared, which we don't have that we can get rid of. But luckily, the calculator will do integration for us when we don't have a way of finding the antiderivative in the evaluation. So let me show you how to do the integral on the calculator on the TI. If you don't have the TI, you can also do it on GeoGebra. You can look up the appropriate commands for that. But you would just enter the fnint function, and then depending on which version of the calculator you are using, it might put up an integral, or it might just put up the commands that you would use to do it. If it puts up the commands, here they are. And if it puts up the integral symbol, you just plug in the numbers and the functions in the right spot, and everything will work out. So this is the integral from 0 to 12 of 48x divided by the square root of x cubed plus 12x plus 4 dx. Notice we just changed them all to x's. We compute this, and then we divide by 12, and we get a number of 15.042. And because this was in thousands, that means it's $15,042 per month. That's the average amount of sales for my new toaster.